I'm Rai Kookana with CSIRO Land and Water based here in Adelaide. I want to acknowledge the contribution of my colleagues here, Joan and Mike, who are the chemists at CSIRO, and also Peter Gunnan at EPA, who's been applying some of the work which we have been doing in the real world. So following on from Shalini's talk, I just wanted to share with you some of the work which we are doing with the wastewater chemicals to establish if we can use some of these chemicals to establish link between the source, wastewater as a source of contamination in surface water or groundwaters. So what I'll do is give you a bit of background about the tracers and share some of the overseas studies on surface water and groundwaters, and then follow on with a couple of examples what we've been doing in Australia. Probably I won't have time to talk about sample preservation, but if you wanted to know a little bit more about that later, and finish off with potential applications. Obviously, wastewater as a resource, and as Shalini mentioned, the pressure on recycling and reuse of water for water security, food security, so there is greater reliance on recycle and reuse, but then that could lead to contamination issues with water and food. And there are a number of possible scenarios you could think of, either from water perspective or from food quality perspective, where the industrial or human activities in one form or the other can lead to contamination. But the question here is, can we use those myriad of chemicals which are present in wastewater with the ability now that we have with analytical tools which are so sensitive, can we utilize some of those as markers and tracers to establish a link with of the contamination with a particular source? And that's the focus of this talk. So first question is, what will make a good tracer? So with so many different possible contaminants are there, or chemicals which are present there, the key thing is that the marker, the tracer, has to be persistent. It needs to be conservative and persistent so that it's going to stay there for long enough time for you to kind of establish that link. It needs to be mobile. It needs to be moving with water. If it's significantly retarded because of attachment or other processes, then we are not going to see the real true reflection of the extent to which that water has moved. Specificity in terms of source. The chemical has to be reflective of a particular activity or a source, type of source of water. And also importantly, that we should be able to detect it, which means it needs to be high enough concentration compared to the other chemicals or the chemical of our interest. At the same time, we need to have robust and routine analytical methods so that we can detect them. So the detectability, those are some of the criteria we used in relation to also a project for EPA where we looked at different industries and identified different chemicals which might be used as markers or tracers. So why artificial sweeteners? Because when you think about beverages or food or candies or whole set of food materials or products, widespread usage, and its usage might even increase with the pressure on sugar and calories and all sorts of things. Because of the high, relatively high sweetness, if you like, compared to natural sugar, and also the calories sort of being calorie free, that's where the number of products which have been using artificial sweeteners. It's several billion dollars of industries globally, but within the suite of artificial sweeteners which are used in different products, there are some which are very persistent and good compounds for use. For example, S-sulfane and sucralose are the two artificial sweeteners. They will pass through the wastewater treatment process. On the other hand, natural sugar would be removed quite effectively. So they are contaminants in their own right, but more importantly for today's talk, we should be viewing them from the point of how we can utilize them for the purposes of markers. This is a list of some of the artificial sweeteners. On a cola or a beverage or other product, you won't see the name, you would see the additive code. So basically a particular code reflects a particular compound. Some of the product brand names associated with these compounds are listed here too, and the chemistry. So majority of those are such that they really don't interact with the environment very much, and you could utilize them and effectively for these purposes. Just to give you a couple of examples from overseas, this is a study in 2011 from Switzerland, where they were particularly interested in perfluorinated compounds. These are fluorinated compounds becoming a major problem in the environment, particularly because of their widespread usage, and more recently with respect to the firefighting foam. But they're used in plating and even in your kitchen with your Teflon coatings and all that sort of thing. So the perfluorinated compounds was the main focus of this study in Switzerland, and they wanted to see the link of PFOAs with the population, and also relationship between the concentration of sweetener and the concentration of these perfluorinated chemicals. And they found that acesulfame, one of the sweetener, had a very strong link with the concentration of perfluorinated compound, as well as its concentration dependent on the population density, so a good marker of population. So for that study, it served the purpose quite well. Similarly, another study from Germany by a former CSIRO colleague, Wolf, and that's to do with the groundwater sources. And there in a 6-year monitoring study in several areas where there was a suspicion of the leakage of sewers contaminating groundwaters, and they looked at a couple of different compounds. One is the acesulfame, which I talked about, artificial sweetener, but also a pharmaceutical compound, an anti-epileptic drug called carbamazepine, which we detect here in Adelaide and elsewhere quite commonly. And both of these compounds are very persistent. Carbamazepine is highly mobile, wouldn't break down easily, will pass through the treatment plant, and you can use that as an effective marker. So in this study, they could see that the places where the groundwater was contaminated with the leaking sewers, they could find both of these markers. So you could basically choose a suite of compounds to do the job. We have at CSIRO in Adelaide been developing methodology for a whole range of these markers, particularly stripping it out of the water through a solid phase extraction technique, but then using LC, liquid chromatography, with the tandem mass spectrometry, and do that effectively. Very briefly, just to show that basically these different compounds elute at different times, and we can do them quite sensitively, considering their presence in environment is quite high concentrations often. I want to show you an example where we applied this technique in Queensland, Lockyer Valley, where the issue was whether some of that recycled water would have contamination of groundwater or not, and we were also interested in other chemicals of similar nature which might be present. And so Leif Wolf, a colleague, is basically did this study where we have in Gatton a treatment plant, and then the surface water and groundwater contamination happening with that. There was a whole range of compounds which were selected, pesticides, pharmaceutical compounds, and the sweeteners. And I'll show you a couple of graphs specifically for the sweeteners. Or first on carbamazepine, which is the pharmaceutical drug and a persistent one and commonly used as a tracer. So in here what we have is basically the treatment plant, which is a square box, red one, and then you have surface water, which is triangles, and the groundwaters, which are circles. So depending on where you are, you find carbamazepine present in surface water as well as groundwaters at different places, which is indicative of that wastewater treatment plant recycled water is actually recharging into the groundwater, and you could establish, based on the concentration and presence of this compound, the extent of that level of contamination or recharge. Another compound which often people talk about, caffeine. Caffeine is another marker, but in this case we found caffeine in surface water but nothing in the groundwater. And that's not surprising because caffeine breaks down fairly rapidly in a biologically active system. So caffeine, while it could be detectable in surface water system where there is a longer time involved in relation to transport, etc., it might not work very well. So relationship between different compounds, and particularly the artificial sweetener S-sulfame, we found quite a good. Wherever there was a higher presence of carbamazepine, we had a higher presence of S-sulfame, and similarly other contaminants. So again, it's pointing out that we can use the artificial sweeteners or compound like carbamazepine as a good environmental tracers. Just finishing off with potential applications, obviously wherever there is a surface water, groundwater interaction situation is there, and wastewater is a source, you could possibly utilize these compounds as a marker. And you could think of various situations. We have applied in Adelaide with some councils where the sewer outflow happened and surface water got impacted, and it was suspected, and with the help of artificial sweetener we could establish whether that was the case or not. You could think of septic tanks leaking, groundwater contamination. People have used it for landfill leachate and groundwater plume demarcation type situations. Effluent from certain industries. You could follow that up. There was a case in Adelaide where somebody actually discharged or deliberately released a lot of unused cola in surface water, and we could establish that through the obvious high concentration of the sweeteners there. So it's a good indicator of population impact, and it could be a good indicator of the anthropogenic activities in situations like that. So with that, I'd like to acknowledge some of the colleagues, Wolf and Darren, Leif and Darren in Queensland, and also EPA here, Sean Thomas, as well as Peter Goonan, who has basically given a few different situations, and also with some of the councils we worked. At the moment, we are working with Melbourne Water in the Yarra River monitoring study, where the artificial sweeteners are used as an indicator or as environmental tracers. Thank you very much for you.
We've got time for one question, so it looks like it's Roger.
Thanks. That was very interesting talk. Have you done any studies where you tried to quantify the flux of leakage through a sewer network into say groundwater?
I haven't, but one of the study which I mentioned from Germany, and that's where Life actually has done that. So there was like a part of a bigger study where they were doing that. So I can send you that particular paper. That would be useful.
Because that's where it started getting interesting.
She just took the form, but she hasn't.
Exactly, in terms of quantifying the flux. I think with the artificial sweeteners, given the strong linkage with the population, you would probably be able to expect that sort of relationship coming through.
She's going to sign.
Yeah. Okay.